registers to different variables in a code region, which could be a function or a bigger region. And the basic objective is to make sure that we do not have any redundant load store, and the allocation is consistent in the sense that there's no point where the two variables which are conflicting are allocated the same registers. And we did study a simple heuristic based on possible savings within a basic block, and primarily focusing on the loops for doing this global allocation. Now I'll move to one of the most widely used algorithm for doing this, which is known as Chaitin's algorithm, for the person who actually formulated this and provided the solution. So this is done in terms of a graph coloring on the register interference graph. That is, which says what are the variables which conflict at different points, and a edge in this graph connects two live ranges that interfere or conflict with one another. That is, there is at least one program point where both of these variables are live. Then we will connect them using an edge, which mean that they do interfere at that point. Now, once we have the resistor interference graph, naturally we can uh, represent it either using adjacency matrix or adjacency list, because rest of it is actually solving the graph problem. And we try to assign colors to the nodes such that two nodes connected by an edge are not assigned the same color. The standard graph coloring problem. Naturally, the number of colors available is the number of registers that are available for the machine. And a K coloring of the interference graph is mapped onto the allocation of K registers, which is a very simple formulation. So here are just sample graphs having 4 nodes. So what means that these 4 nodes are 4 variables, and these edges say that they are interfering, and when there is no edge, there is no interference. So it is easy to see that this graph on left is 2 colorable. We are being able to use 2 colors and color them, whereas the graph on right is needs 3 colors to be colored, because you have a click which is of size 3. So obviously, if you have a click of size P, then naturally you will always need at least 3 colors. Here we need 3 colors. It is 3 colorable as shown. Now, the basic idea behind Chaitin's algorithm for coloring, which is a heuristic one, because graph coloring, as you know, is a NP hard problem. So the heuristic goes in this way, that we arbitrarily choose a node whose degree is less than K, and put that node in the stack and remove it from the graph. And as we remove that node, as we remove that vertex, then all edges that are connected with that vertex are also removed. So this may consequently decrease the degree of some other nodes and cause some more nodes to have degree less than K. Now, if at some point all vertices have degree greater than or equal to K, then naturally coloring by this algorithm with K colors is not possible. Right? So then we will need to spill some node. We will come to details of that, which basically spilling means that we'll have to choose a node or a variable in the program which cannot get registered. So it will reside in the memory, and every time we use it, we will have to load it from the memory, and every time we define it, we'll have to store it back to the memory. Now, first, let us assume that we have a situation where no vertex needs to be spilled. So in the process of removing nodes from the graph and pushing them to the stack, will eventually be able to remove all vertices from the graph. And once that has been done, then we successively pop the vertices from the stack one after the other. And we start coloring them with a color which is not used by its neighbors. And naturally reuse colors as far as possible, right? So this is a simple algorithm. So let us just have a quick walkthrough through this simple graph. So here is a graph of 5 nodes, and we assume that I mean, it is quite obvious that it cannot be colored with 2 colors. So we try to color it with 3 colors. So the first step is we will choose a vertex which has less than 3 neighbors, right? Degree less than 3, k minus 1. So here there's only one right now, which is node 1, which has degree 2. So we remove this node 1 and put it to the stack. Remove node 1, put it to the stack, and I'm just changing the color and the edges that are removed differently so that we can easily understand. Now, once this has been done, we can see that 2 more nodes, node 2 and node 3, now have less than 3 neighbors. So any one of them arbitrarily can be removed. I remove node 2, and as you can see in this slide, node 2 has been made blue, and the adjacents, the edges incident on node 2 are also removed. So we get this modified graph. So where actually all 3 of the nodes have less than 3 colors, less than 3 degree. So I can arbitrarily remove any one of them. I remove 4, let's say, and this is the remaining graph of 3 and 5 I get. Yes, if you please mute while you yawn, it would help, please. And finally, I'm left with only one node, which I remove and put back to the stack. So in this process, we have been able to remove all the nodes without requiring any spilling. So that clearly tells that the graph is 3 colorable. So what are the colors that I do actually? So I start popping the nodes. So I pop 5, and these are the 3 colors that I'll use, some purple, brown, and green. So I pop 5 and arbitrarily give it color green. Then I pop 3, and it was connected with 5. So I give it a different color, say color brown. Then I pop 4. It is connected to 3 and 5 both. So I need to give it a third color. So I give purple here. Then I pop 2, which is connected to 4 and 5. So I need to give a color different from purple and green. So I reuse the color brown. And finally, I pop 1, which is connected to 2 and 3. I give it the color purple. I could have given it the color green also. That will. So the solution necessarily is not unique. So now I have a 3 coloring of this graph, and that is the basis for the Chaitin's register allocation algorithm. Right? So what are the overall steps for the allocation? We will identify the units for allocation, right? And we will do one step in which we will rename variables or make symbolic registers in the intermediate code such that each live range has a unique number. In general, what can happen? A variable will have a live range over certain program points, and then it becomes dead. And then another definition of that variable will start a second live range, and which will continue for some program points and so on. So a variable may be associated with multiple live ranges. Now, to make the problem simple to analyze, what we do, we actually rename the variable so that each one of them will have a unique life range. Right? I'll show the example. Then once that has been done, then we can build the interference graph. And after we build the interference graph, we can coalesce by removing unnecessary move or copy instructions if they're there. Then we color the graph and thereby select the resistors. Right? Now, if it is colorable in the given k colors, that is, it is solvable in k resistors, then we are done. Otherwise, we will compute some spill cost, simplify and add the spill code till the graph becomes colorable. Right? So we will show this step by step. So these are the overall steps. These are just written here. Renumber, build, coalesce, spill the cost, simplify, spill code, come back and renumber again, because once you have spilled, it becomes a different graph. We'll show the steps. First, the renaming. Now here, what we see is A is defined in these two blocks and is used here. Okay? So, and after that, it is again redefined at this point. So in the middle block, between the use of A and the definition of A, again, this variable A is dead. So what we do is we rename this A on top as S1, let's say. So that's a live range. So S1 is defined either here or here and then used. And the second one, where A is defined and then used in the other two blocks, we call them S2. Okay. So let's take a code and see how do we do it there. This is the original code. You can see simple code. And what we try to put is we put the range of liveness. So you can see X is defined in 1, used in 3, used in 4, used in 5, and then redefined in 6. So the X that is defined in 1 is live till 5. So we say it is 1 to 5. Similarly, Y, which is defined in 2, so it has a range which is 2 to 5. W, which is defined here, does not have a use in this overall range. So its liveness is 3 to 3. Z, similarly, is defined in 4, used in 6. So 4 to 6. U is defined here, not used later. 5 to 5. X is again defined here, a second range for X, and that starts at 6 and goes into G. So as we do this, we now put renumbering as S1, S2 like that. So X here is renumbered as S1. So X in statement 3 is renumbered as S1, X in statement 4 is renumbered as S1, X in statement 5 is renumbered as S1. But then it is a different range, so I call it S6. Right? In this way, the renumbering is done, and I'll have the code in terms of the symbolic registers for which I will need to find an allocation. Now, so based on that, so once we have that, we form the interference graph. I'll not go through every step, but you can say for example, S1. S1 is live from 1 to 5. 1 to 5. So it interferes with the S2, S3, and S4. Right? It does not interfere with S5 because it is used and becomes dead. Right? So with S1, I have a link to S2, I have a link to S3, and I have a link to S4. I do not put a link to S5 because I don't need to remember S1 after the statement 5. So the register given to S1 can be reused in statement 5 itself. Similarly, S2, which ranges from 2 to 5, will have an interference with S3 and S4. Interference with S1 is already been established from S1. So, and finally, when you have S6, since its line range is not closed yet and does not interfere with anything in this region, so S6 does not have a neighbor. Now, so this is the graph that we get, and if we follow, I have not shown the steps of the Chaitin's algorithm, but if we follow the steps, this is one of the possible tree coloring of the graph. And you can clearly infer, because you have multiple 3 clicks, 2, 3 clicks. So you can infer that you cannot do it with less than 3 colors. Here it is very obvious. So this is an optimal coloring of this graph. In fact, while we construct this, we can also put some additional constraints. For example, we can say that the interference graph, we can say that I do not want Z or S4. Let me go back. Z is S4. Suppose I want to say that I do not want this particular variable to be in register 1. Right? You will need this kind of constraints when all your registers are not necessarily general purpose. So maybe some statements, some 3 address statements cannot be done in a certain register. So this just I'm trying to symbolically show you. So I have the interference graph of the symbolic registers. There's the interference graph of the registers that we are going to use, R1, R2, R3, obviously. Each one of them interfere with the other 2. And I add that link between S4 and R1. So it says that if I want to 3 color this graph, or if I want to solve this problem of register allocation with the constraint that Z cannot occupy register 1, then this entire graph has to be 3 color, which in this case it happens to be. Fine. So once this has been done, then we know the colors. I go back. So S1 is R1, S2 is R2, S3 is R3, S4 is R3 again, S5 is R1, and S6 is R2. Right? So those are the mappings here, and this is a code I had. So now I replace S1, S2, S3, all these by R1, R2, R3, and you can see that instead of 6 symbolic registers with 3 registers without no speeding, we can solve this allocation problem. Right? So that is the basics of the algorithm. Let me show you another example. Let's say this is the graph, and at every point we have shown the liveness. So for example, on input to the first block here, B, C, and F are live. Right? B, C, and F are live because they are used without being defined. So they must be live on entry. Whereas A and D are not live because they are defined and then used in the block. So very simple. So the liveness DFA will generate this kind of. Now, once we know that at the entry, the BCF is live, then within the basic block, I can say that between the assignment of A and assignment of D, only ACF are live. Right? A has become live because you have defined and you are going to use it within the block. B is live. B is not live because after this use, B is not used in the remaining part of the basic block, nor B is live on exit. Here you can see that on here, the live variables are CE, here is CDEF, so B is not there. So B does not need to be live anymore. So I say this is ACF, this is what is live. After the next statement, A is no more live Because A has no further use in the basic block and not live on exit, A F remains live because it still has a use, D remains live, it has a use, and C remains live because it also is live on exit. So CDF will remain live because they are live on exit as well. So in this way, the liveness of at every point is computed. Right? So using this now, we can, using this CFG now, we can compute the interference graph. Right? Now, so there are 6 variables. So there are 6 nodes, A, B, C, D, E, F. You can see that in no place, in no set, A and B occur together. So there is no node with edge between A and B. Whereas here, let's say BCF, B and C occur together. So we'll have an edge between BC, CF, and BF. We'll have a click in that. We have 4 variables occurring together here. So we'll have a 4 click. 4 variables occurring here, we'll have a 4 click. But again, let's say there is no set on which I have B and D occurring together. Nowhere. So there is no edge between B and D. Okay? So this is my resistor interference graph. And so my next step would be to color it and get the resistor allocation. So obviously, here it is actually trivial that I cannot have a coloring with less than 4 colors because there are 4 clicks. There are 2 4 clicks actually. So 4 colors is the minimum that I can infer here. So let me try to do a 4 coloring of the graph, and I will follow the same stack algorithm of Chetin, and I'm not showing the steps here. If I do it, then I have a 4 coloring, which is not unique. You can change the colors, that is the resistors, but this is one coloring where F gets R1, A and E gets R2, D and B gets R3, and C gets R4. You can say this is consistent. So we have been able to find a 4 coloring of this graph. So therefore, the allocation is possible with 4 colors or 4 resistors in this problem. Okay. So here the example is worked out. If you want to go through that, A and D will be first removed. So this is a stack where leftmost end in the top of the stack. So first you remove A, then you remove D, and then you come to a click. So you remove them in certain order, C, B, E, F, and you get this stack. You do the pop, and you get the coloring. So with this coloring, this is the original graph I had, control flow graph. This is my, on right is my interference graph. So with this, now I can rewrite the code in terms of 4 resistors instead of 6 symbolic resistors that I would have had. So 4 resistors, and the problem of global allocation is solved in this case optimally. Let me stop at this point and see if there is any question. Any question, friends? No questions? Everything is too easy? Good, of course. So let me go back. Okay. So now the interesting thing happens that if our heuristic would fail at a certain point, that is, if we get to a state where all nodes have k or more neighbors, right? So let us try that. We have seen that this graph can be colored with 4 colors, and we have also a sample logic of 4 click to say that it cannot be colored with less than 4 colors. So let us try coloring with 3 colors and see how it fails. So with 3 colors, if I go back to the earlier slide, with 3 colors, A has less than 3 neighbors. So I can remove A and get this. And now I'm stuck because every node has either 3 neighbors or actually 4 neighbors, more than 3 neighbors. So I cannot color this graph in that way anymore. So what I'll have to do, I'll have to spill a node. We'll pick a candidate node and spill it for temporary live in memory. And let us assume that F is picked as a candidate. So if F has been spilled, then what I do is I remove it from the graph because it is no more going to take a register. It is going to be in the memory. So it has no interference with any of the registers. So I'll spill and remove that. And with that, now I have this graph, right, which is 3 colored. I remove B and then D and then E and then C or some other order. And I have a 3 coloring. So if I put back onto the earlier graph, then I have 3 coloring for B, C, E, D, and F was spilled, so it does not have a coloring. So for the spilling, what we'll do? We will, when we fail, we will spill one of the nodes. Here we are spilling F. We must allocate a memory location, which is the home of F. And typically, this is done in the current stack frame. So we call this address FA. Just so that it will now have to be in a memory. So we will have to allocate a memory location for that. So I'm calling it FA or F address. So before every operation that will use F, I will not get the value of F in any register because I've spilled it. I'm not being able to find a register for it. So what I'll have to do, I'll have to read that value, load that value from FA. So F gets load FA. And similarly, after each operation that defines F, if F gets changed, then I will have to store this value back to the memory, right? Because there is no register. So I will have to introduce this load and store for F at every point where it is either used or it is defined. So now I change my code. You can see here F has a use. So before that, I introduce a load statement, F assigned load FA. Similarly, here in the block on left, I have F assigned to by 2 times E. A new F is computed, so I have to update the memory, store F to FA. The block on right has no F. Block below has an F which is used, so I have to load F. So I have now changed the code by spilling. It becomes a new code with some loads and stores. So what I'll do, I will recompute the liveness information based on what I have. So what will the liveness? This is on right is the graph, original graph, which had the liveness. Now, F will be live only from its definition here and its use here, right? So CDF. But it is not live on exit because if you trace back from this last block, it does not need to be live because it is being defined, which means in the exit of the right block, it does not need to be live. It is removed. Which means in the previous statement, it does not need to be removed, need to be live, which means on entry to this block, it does not need to be live. Similarly, F is being defined here, so it is not live on this path either. Which says that F is defined and used within this topmost block, and it is not live on exit from the block. So I remove that. Similarly, when I look at the last block, F is defined and used here. So it is live in between, so I get CF. F originally was not live here, so that's already there. It was live on this path because I needed it to be live at the entry to this block. But I don't need that because I'm defining F before using it. So F is not live at any of these 2 points, so it does not need to be live at the entry to this block either. So it is removed from. So with this, at a number of points, F gets removed. It stays only at 3 points. Here between load and the use, between its definition and store, and again in its load and use. So the new liveness information is almost as before, but with the changes that I have explained. So F is live only between its load and the next instruction, and between store and its preceding instruction. Okay? Now it may so happen that F may be used on consecutive instructions, or it may be used multiple times before being redefined. So you will have multiple loads for the F, which can subsequently be removed, which can subsequently be optimized. So in terms of our model, what does the spilling do? It basically reduces the live range of F. Earlier it was spanning quite long. Now it is very limited to the load and use and definition and store. So that will reduce the interference, which will result in fewer neighbors in the register interference graph. So now if you look at, this was on right, this was the original register interference graph. And with this change, naturally F, as we see, is no more interferes with A or with E. It just interferes with C and D, which happen in between. So if you look at this, it is very easy to see that the resulting graph is 3 colorable. You can remove A, you can remove F, you can remove B. And once you have done that, you have a 3 click. So you can remove them one by one. So by 3 colors, obviously this can be colored. So the additional spills might be required before a coloring is done, because it may so happen, for example, coming back. For example, if I wanted that this be 2 colorable, if I was having just 2 registers and I want this to be 2 colorable, then even with this spilling of F, I will not be able to actually color this graph. Then I will need to do further spilling. So in this way, I'll be able to come to a point with multiple spilling, which fits into the number of registers that we can actually have for allocation. Now, naturally, there is a question. Let me just go back. If you look into the original graph where we were unable to do a 3 coloring, the question is, which of these different nodes should I spill? Now, we did spill F. We could have spilled E also. We could have spilled C also. Now, naturally, a heuristic will tell you that it makes sense to spill that particular node, which has kind of more number of neighbors, so that you will have maximum reduction in the interference of liveness that could be. So we say that spill temporaries with most conflicts. So if you look into this, then F 1, 2, 3, 4, 5, 1, 2, 3, 4 for E, 1, 2, 3, 4, 5 for C. So if you look into that heuristics, then F and C will be the prime candidates for removal as a spill. Okay. Then the other, if we go back to the code, let me go back to the code. If we go back to the code and see here, then we see, okay. So I would prefer to spill that variable which has less number of use and less number of definition. That's the heuristic, because every use will introduce a load and every definition will introduce a store, right? So if I had applied that heuristics, then instead of spilling F, which actually has 2 loads and 1 store, I should probably have spilled C, right, which has only 2 loads. That may have been better, but it depends. You can try to spill C and see what kind of effect you get. So this is the second heuristics. So the first is to get maximum benefit by reducing maximum number of conflicts. The second is heuristics is to think that how to minimize on the load and store by choosing variables with fewer definitions and use. And certainly the last but the most important heuristics is we should not spill variables which are in the inner loop. Here you have only one loop, but if you have nested loops, then you should avoid spilling in the inner loop for the same reasons we have seen earlier, because inner loop is more frequently, more regularly executed. For each time of the outer loop, the inner loop will have to keep on doing the spilling, so the cost will be more. And since after the spilling, we are recomputing, we are putting this load store and recomputing the graph. So any heuristics that you choose will be correct in terms of allocation, but some may do better than the other in terms of the number of additional load store that may be required. And then once this has been done, then we can scan, and if there are unnecessary load store that have resulted, then we can try to remove those as well. Okay. So that is about global register allocation. So let me see if there are questions. Any questions on global register allocation algorithm of Shetty using graph coloring? No? Okay, good. So we have now, in terms of the backend code generation, we have now done 2 of the major steps. One is optimizing the 3 address code, which we have done at the basic block level, and also doing the DFA and trying to do the optimization at a global level. And then we have looked into the register allocation problem, and we have tried to allocate registers globally, which in some cases will be optimal, in some other cases will not be optimal. So our next would be, let me introduce the problem, then we'll discuss the details tomorrow. Our next would be to generate code. So in terms of generating code, what are the main issues? One is we will have to transform the intermediate code to the machine code. So instruction scheduling or instruction choice is a typical question that you will have to solve. And obviously, we assume that the quads are available, the 300 statements are available after all this optimization and all those. The control flow graph is available, and the symbol table is available. But if after that, there is a choice. For example, suppose I have a quad A assigned A plus 1. Now, this, for a particular processor, for this, I may generate increment A, which is actually what it is doing. Or I can do an actual addition code, that is load A into R1, add 1 to R1, and then store R1 back to A. Naturally, one sequence is faster than the other. So we have to take this cost implication in the choice. The second is what is the order of code generation? Some orders may use fewer registers and maybe faster. Question also may be which registers to use. As we have seen, optimal assignment of registers to variable is difficult to achieve. So we may have to make choices along with the instruction scheduling to have a workable solution with a good number of assignment. May not necessarily be optimal. The other question that I had mentioned earlier, that while we finally generate the target code, we need to see what are we optimizing for. Are we optimizing for time only? Or we want to optimize for memory, we want to optimize for power. So our algorithms, and you'll find that most of these algorithms in the optimal case are NP hard. So we will certainly be doing certain heuristics, and those choices depends on what we are optimizing for. So what primarily we have been talking of so far was trying to optimize time, but I might want to optimize memory or power. Another good question is the code generator easily retargetable to other machines? That is, often you need, when you write a compiler, you will need to have that compiler for multiple platforms, say for x86, 32-bit, 64-bit, AMD variations, then alpha processors, and so on and so forth. There could be several such. Certainly, you want to use strategies which can very easily retarget that code. So that retargetability is a basic question. So these are the things that we will have to look at, and we will do that in the next class tomorrow. If there are no further questions, then I will stop here, because I do not actually want to get started we have only just 10 minutes, because we'll have to present through the entire algorithm of these issues. Quickly, if there is any question, let me answer. Otherwise, we'll stop here. No questions? Everybody is asleep? Anyway. Okay then. So we will stop here, and we'll meet at 8 o'clock tomorrow and discuss about the old generation process.